Okay, thank you. I think we will start with the second talk of today. So we have the pleasure of having Désiré Kédagni that's gonna talk about marginal treatment effect with misclassified treatment. You have 40 minutes.
Thank you, Ismail. Thank you for inviting me to this workshop. I'm having a great week so far. Thank you, Thomas, and all the organizers. So, yeah, I'm Désiré Kédagni from Iowa State University. So in the summer, I'm going to join the University of North Carolina at Chapel Hill. So this is a joint work with Santiago Asenriza, who is now an assistant professor out in Uruguay. And Ken Honban will be on the market next year, and he's doing well. So marginal treatment effect with misclassified treatment. So I will start with this statement from a paper in Restart by a colleague of mine, Brent Kreider. He says that even in the homogeneous treatment effect framework, measurement error in binary regressors will result in severe identification deterioration of regression coefficients. Okay, even if you take the simple linear OLS regression, and then the treatment variable is binary and mismeasured, you will lose identification of the coefficient. Okay, and the problem is severe in the treatment effect where you have heterogeneity in the effect. Okay, so I'm going to consider the IV model. Okay, so in this literature, the first paper to really investigate the consequences of measurement error in treatment variable when we allow for heterogeneity is the paper by Takuya Ura from UC Davis. He's the first to provide bounds on the local average treatment effect, also called the complier average causal effect in statistics. So there is this paper by Zhang and Deng, where they derive bounds on the lates in the binary IV model, where all the outcome variable, the treatment variable, and the instrument, they're all binary. But they consider the framework with non-differential measurement errors. Here I'm going to allow for differential measurement errors, okay? And we're going to look at a different object called the marginal treatment effect. I'm going to introduce that object. Okay, what we do, we derive bounds on these objects, okay, under the same set of assumptions that Takuya Ura has in his paper. And we show that if you look at the lates in our framework, we're going to show that we get tighter bounds on the same object that he looked at. We're going to show where the improvement comes from. And more importantly, we're going to show that the bounds that we get can identify the sign of the marginal treatment effect locally. Okay, so usually one criticism of the bounds is that they are not informative, right? Here we can show that always we can get the sign locally. I will explain what I mean locally. But the late is a form of integral aggregation of marginal treatment effect. So even though you can be able to sign the MT for local values of the instrument, when you aggregate them, you may lose the sign. Or that's why when you look at the late, you may not be able to say what is the sign of the late, but for the marginal treatment effect, you can tell the sign, okay? So I'm going to show some illustrations through numerical and empirical design, okay? Questions? So this is the model. So we're going to spend a lot of time on this slide to make sure that we understand what we're doing. So I observe an outcome variable Y, okay? And then I have a treatment variable D star, which is not observed, but instead I observe D. So you can think of Y as your earnings or wage, and D being whether you have a college degree or not, okay? So when in the survey, I ask you, do you have a college degree? You tell me yes or not, right? I have no way to check whether what you're telling me is the truth, okay? You can just misreport, even if at some point you drop out from college, you tell me that you get a college degree. So this star would be the true, okay, indicator for college degree. And D is what you report to me, what you tell me. In the data, I see Y, your earnings, I see D. And then we're going to assume that the decision to go to college is a cost benefits decision. You look at your cost, which will be V, and you look at your benefit of going to college, which will be this function PZ. So when your cost is less than or equal to the benefits, then you make the decision to go. That will be an assumption here. Yes. Epsilon?
The derive.
Yeah, I'm going to talk about epsilon in a minute. Yes, yes, good question. So this star, the decision is just such that when V is less than the PZ, this star is equal to 1, otherwise this star is equal to 0. Now, the epsilon is the misclassification, the misreporting, indicator for misreporting, okay? So when epsilon is equal to 1, then I see D equal to D star, D equal to 1 minus D star. And when epsilon is equal to 0, meaning that there is no misreporting, there is no error, measurement error, then D is equal to D star. So this representation here is not an assumption. When we take any two binary variables, you can always write down this representation, okay? So now the assumption that you're talking about, whether epsilon is independent of D star, no, we're not going to require that, okay? But we're going to discuss all the scenarios. So we're going to look at the case when epsilon is independent of D star, and we're also going to look at the case when epsilon is not independent of D star, okay? So in this literature, when you have binary treatment variable, it is well known that the measurement error can only be non-classical, in the sense that the measurement error cannot be independent of the true treatment. And that's happening here. When you look at D, you can write it as equal to D star plus 1 minus 2 times D star times epsilon. Then the measurement error is this 1 minus 2 times D star times epsilon. So as you see, this measurement error is negatively correlated with D star, and that's well understood in the literature, okay? So the object of interest would be the expected value of Y1 minus Y0 given this value, a value of V. V is the unobserved variables that drives the selection into treatment, okay? So if we think of it like in the late framework, you can think of the V here, the unobserved variables that drive the compliance type, the compliance status, okay? Whether you are a complier, an always taker, or a defier, right? Now, why would this object be of interest? If you look at the setting of the late, the compliance setting, right? We have this V variable here, okay? Assume that my instruments here, the C here, we'll talk about that soon, it's binary. Then assume that P0, P1 here. In the standard local average treatment effect setting, this population will be the set of compliers, okay? So when you try to identify the late, you are looking at these people. Here you have the always takers. Then you have the never takers here. Okay, now within the set of compliers, it's possible that some people have positive effect, some people have negative effect, and even some people have zero effect. If you look at the late, you may not detect that. But if you look at the marginal treatment effect, you may see this heterogeneity that otherwise you will not get through this local average treatment effect. Questions?
What is the symbol P of Z?
The P of Z here is what I call the benefit function, but in the late framework will be just the propensity score, the probability of getting treated. Yes. So the P of Z, if you think about it, if you have the instrument is valid, right? in the sense that it's independent of V and Y1, Y0. The probability of getting treated, if we normalize the distribution of the V to be uniform, it will be equal to the PZ. Okay? Questions?
Yes, I have a question. So are you going to be implicitly conditioning on values of V that designate compliers so that your marginal treatment effect is equivalent to late, or are you going to be extrapolating to always takers and never takers?
Yes, that's a great question. So this is the case where you have a binary instrument. But now when you have a continuous instrument, then you can define, let's say you take Z1 and Z2. You can define the compliance with regard to this pair, right? And then for late, you can be able to get this. But with the marginal treatment effect, with respect to this pair, I will be able to say something about the value here when I have a continuous instrument. So you can decide to have multiple lates based on the pairs that you consider. But if you look at the marginal treatment effect for some V outside here, it's possible that you identify the effect when they are in the support of the propensity. And that's also one advantage of looking at the marginal treatment effect. Okay? Questions? Okay, so I'm going to show you why the marginal treatment effect is also important. I just introduced that through this explanation. But you can get all the other parameters through the marginal treatment effect. Once you have the marginal treatment effect, you can integrate over the marginal treatment effect with a weight. Here, the weight will be 1. If you integrate over the support, okay, then you get the average causal effect or the average treatment effect. And you can get the average treatment effect on the treated also by integrating the marginal treatment effect with an appropriate weight function. So all the traditional parameters that we look at in causal inference, we can get them through this marginal treatment effect. And more importantly, suppose that a policymaker wants to induce people, okay, into college in order to think that, okay, maybe income is low, we want to encourage people to go to college. So if we induce 20%, okay, of people who do not have a college degree, we induce them to go to college, what will be the effect on earnings, right? So usually, if you use late or average treatment effect on the treated, you may not answer this kind of questions, which may be relevant for a policymaker. Say that I want to induce 20% of people who are not vaccinated to get vaccinated. What will be the effect of such a policy on the outcome? Okay. So there is a parameter called the policy relevant treatment effect parameter that can help answer this question through the marginal treatment effect. So that's why I think it's an object that is not popular yet in statistics and quantum physics, but it may help answer some questions that are relevant for a policymaker. Questions? Okay. So here is an example.
Just a quick question, Désiré. Yes. So the identification of the marginal treatment effect will require a continuous IV, right?
Yes. So I'm going to come to that in terms of when I state the assumptions. We need the continuous IV to be able to say something for people here at the margin. Otherwise, you can only identify the late type of effect. Okay. Questions? Yeah.
So I mean, I think I know the answer is good, but of course, once you have all these marginals and you take these integrals, you can define things. But take your example. I have something that'll get 20% of the people who are unvaccinated to get vaccinated, or 20%, right? The exact shape of that distribution is going to matter a lot, because you might, it might be the 20% are the ones who are being careful anyway, and so or you might have something else that'll also get 20%, but the right 20%.
Yeah.
So you're assuming a lot of knowledge of the exact shape of that distribution.
Yeah. So I'm going to know the distribution of this PZ function And that will matter a lot. How many people are not treated? How many people are not vaccinated or not? I'm going to show in the empirical example, the distribution. And when I do this exercise, we're going to see what are the people that are moving now that are taking the treatment. Yes, that's important. And that will play a role in whether we are, the effect that we estimate here, the weight here actually will depend on that. Yes, exactly.
But I think the question is a bit deeper than that, because if you define the PRTE, right? So you want to extrapolate from the MT from a particular group of people to another group of people.
Yes.
But this presumes that from a setup to the other setup, the MT gonna keep the same shape.
The MT function?
Yes. Otherwise, how you could do the extrapolation when you're gonna do from one particular environment A to the environment A prime?
Yes, so, but the assumption will be that they have an instrument that do that through the instrument, right? The instrument does not shift this V here. So that will be an assumption. That's why the MT will keep the same function. So I will assume that, yes, under the scenario where I shift people, this instrument is not shifting, but the only thing that I'm changing will be this policy function, this P function, yes. So it is documented that in the US, more than a third, okay, of the survey respondents, they claim to have a professional degree while they don't have such a degree. So if you think about measurement error, I'm going to introduce that. So it's a serious problem. Because of that, you may be getting an effect that is not actually the causal effect. So it's important to care about measurement errors. So, but this could be, it could mean two things, right? Just that people are misreporting intentionally, or just they don't understand the definition of professional degree, right? So we cannot say that people are lying, right? It can be both, right? So, okay, the point is that there is measurement error in survey data, especially when people, it's about like education or whether you are vaccinated or not, whether you wear mask or not, right? People may misreport because of social pressure, right? So the assumptions, okay? We're going to look at the assumptions and then the identification results. Okay. The first assumption is that we have an instrument that satisfies the exclusion restriction. And this is pretty standard in causal inference. The second assumption is what we call extended random assignment. It states that the instrument is independent of all the unobserved variables in the model, right? Including the misclassification variable, okay? So before, the standard random assignment will be that Z is independent of Y1, Y0, D1, D0, this D1 star, D0 star. So here, the variable that drive the selection into treatment is the V. So when Z is independent of V, Z will be independent of D star 1, D star 0. Okay. So because of this structure, I only need my instrument to be independent of this V and then the potential outcomes to get the standard random assignment assumption. But in addition to that, I'm going to assume that the instrument is also independent of this epsilon, the misclassification. Okay. And then the third assumption is that we're going to assume that the V, this cost variable, okay, is absolutely continuous. So we need that. If it's not continuous, it's discrete. We need that we know the support if we want to look at the MT. So this assumption helps normalize the distribution of V to uniform 0,1 over the support. If it's not uniform 0,1, you can apply the CDF of V on each side here, and then transform that to a random variable that is uniform 0,1. Okay, so this is just a normalization. Now we need a continuous instrument. That's the fourth assumption. And why we need this, I'm going to show that in the proof. But we need it to be able to move the Z in a continuous way to be able to get the values for HV. Yeah. Questions? And then the fourth assumption, we're talking about measurement error. We need to know something about the extent of the measurement error, right? So we're going to assume that we know some upper bound, okay, on the measurement error. If we don't know the upper bound, we have no information, then this upper bound will be equal to 1, can be from 0 to 1. But suppose that I go to the universities and then I ask them how many people got a correct degree, they tell me. Then I compare that to what I see in the data and say, okay, the difference can tell me something about the extent of the measurement error, right? So we can have this extra information from extra sources, okay? So this information, we're going to take it ad hoc and say, okay, we know something about the extent of the measurement. If we don't know, then we're going to let this alpha bar to be equal to 1, and I'm going to show you the bounds in that case, okay? Questions? So the identification result, the main identification results, okay? So suppose that we take the conditional expectation of y given this PEC, okay? We fix that. We're going to write it as the summation of these two integrals. The first integral is about the potential outcome for the treated group, and the second integral is about the potential outcome for the untreated group, okay? So what I'm going to do, if I assume that I have a continuous instrument and that this function here is differentiable, I'm going to take the derivative of this left-hand side with respect to P, and then it's going to be equal to the derivative of the right-hand side with respect to P, right? If I do that, you see that this part here just gives me what I'm looking for, my marginal treatment effect. If you take the derivative of this quantity with respect to P, you get the expected value of y1 given v equal to P, right, by definition. You take this derivative here, you get the expected value of minus y0 given v equal to P, because the P is here. And that gives you the object that we want to identify, right? So if you look at this, if I knew this P is the function, then I can estimate this. This is identified from the data. If there is no misclassification, if there is no error in the treatment variable, as I was saying, this PZ function will just be equal to the propensity score, the probability of getting treated given Z, which we can estimate in the data. We know that we can estimate the propensity score. And then once I come here, once I come here, I point to identify the marginal treatment effect. And marginal, as I was saying, we see the derivative. Usually when we think about marginal, we see people at the margin, right? So you have this derivative here, which is identified. You get this object, and it can show you some heterogeneity that you will not get through the compilers average treatment effect. So actually, it's a function that you identify. But now the issue in what I'm doing here is that I don't know this PZ function because of the misclassification. So from now on, what I will try to do is, how do I get this PZ function? Okay. If you give me a candidate for this PZ function, I'm going to check whether this will be it will satisfy the restrictions that the model imposed and keep that. So I'm going to find the possible candidates for this PZ function, and that will be the identified set for the PZ. Okay. So how do we do that? Let's look at this first. So from now on, we try to get the identified set for the PZ function, okay? So let's look at this equation here. Adjust from the law of total probability. Take the unconditional distribution of the V, okay? You can split that between people who misreport and people who do not misreport, just by using the law of total probability, okay? And then the second equation here comes from the first stage, what we call the first stage regression, if you're thinking in terms of regression here, okay? If you look at the first stage equation, you have this D star equal to P less than or equal to PZ. So if this star were observed, that would be my first stage, right? So we just use the first stage. So we want to identify an object from the first stage. So we use this equation. And then we solve for the distribution of V when the person is misreporting, and distribution of V when the person is not misreporting. Then we get these functions. Now, the question is, are these two distribution functions? Not necessarily, right? So we need to make sure that they are distribution functions to be valid. And that gives us bounds on the PZ function. So we need this to be not decreasing. The limit at minus infinity has to be 0, plus infinity has to be 1, and then right continuity, right? So if we use these conditions, then we get the following bounds on the PZ function. But these bounds are for given Z. But now I'm trying to look at the derivative of this object with respect to P, right? So I need the shape of the PZ function, not only the location, right? So I need more than getting pointwise bounds on this PZ function. Right. So from that, now what I'm going to do, I'm going to try to identify the slope, okay, of this PZ function, not the scale parameter, not the location parameter, okay? So, and then we write down the model. What is the information that we get from the whole model, the model that we have? We have for the joint distribution of Y, D, given Z. That we can compute that from the data. Then we are going to match that with the unobservables quantities, okay? The probability, the joint probability of the Y1 and the misclassification given V, okay? Plus this integral, similar to what we had in the beginning, but now we involve the Y's, okay? I do the same thing for the reported control group. They might be in the control group when I see them, but they are not necessarily in the control group because of misclassification. And then there is another condition, which is called the index sufficiency condition. In this model, when you condition on the Z, you get the same distribution when you condition on the PZ. And that's similar to Rosenbaum-Rubin's result that when we think about ignorability, when we condition on X, right, we get the same thing similar if we condition on the propensity score. So the PZ is the propensity score here. So the model implies that the distribution that you observe, okay, you identify, will be the same distribution if I replace the Z by the propensity score. Okay. So these three conditions, they give us actually the identified set for the PZ. But as you can see, this is not tractable. So we're going to work out the analytical bounds for the PZ function. How we do that? We're going to start, I say we want to look at the slope for the PZ, right? We're going to look at the difference between PZ, Z, and Z prime for this quantity that we observe in the data, this distribution that we identify in the data. We're going to take the difference of Z and Z prime. When we do that, we get this. This is kind of the density version of what I just showed you. We get the difference of these two integrals. The first integral involves Y1 and the measurement error, the classification variable. And then the second part involves the Y0 and then the classification variable. Okay. Now we can apply the absolute value of each side, and then it's going to be equal. But when I apply the absolute value here, I'm going to use the triangle inequality. It has to be less than the summation of these two quantities, which gives me this. Then I can integrate each side with respect to Y. Okay. When I take this integral, then you integrate this each side here with respect to Y, you get the probability that someone reports truthfully given V. And then on the other side, you get the probability that the person misreports given V. And the two sum up to 1. You get the quantity now that only depends on PZ minus PZ prime. And then this quantity has to be a lower bound on the difference between PZ and PZ prime. So pay attention to this a little bit. We want to identify PZ which is an object from the first stage regression. But now we can use information from the second stage, the Y side, to try to bound an object from this first stage. Usually we don't have that, right? This is like the outcome variable is helping the treatment variable in terms of identification. Usually don't have this. So we create this lower bound for the PG and PG prime. We're going to use the pointwise bound to get an upper bound. And then the derivative that I showed you is just a limit version when I let Z go to Z prime, right? So that's what we're going to do. We get bounds on the PZ minus PZ prime. Then I'm going to take the limits of these lates for Z prime to Z when I let Z go to Z prime. So the marginal treatment effect is like a limit version of the local average treatment effect. That's how we get the bounds on the marginal treatment effect, the analytical bounds. Okay, so this is the main result. We get if there is this extent of the misclassification is 0, there is no misclassification, we get a limit of the late. Okay, but if there is misclassification, then we get these two bounds. As you can see, we get the mean of 0 and something, and the mass of 0 and something. So we weakly sign the marginal treatment effect for HC. That's what I was saying earlier in the introduction. So you may get this for a particular Z, but when you integrate over to get the late, you don't know the sign. That's why sometimes with the marginal treatment effect, you can see this heterogeneity that otherwise you may not see with the late. Questions? So I'm going to show you some numerical illustration and see how the bounds look, okay? And then from there, I'm going to discuss the assumption when the epsilon is independent of V and when the epsilon is not independent of V, okay? Here, we don't have any assumption for this bound. There is no assumption on the epsilon, except that the instrument is independent of everything that is unobserved in the model, okay? So in this design, we know exactly the PZ function is just the probit phi of 2Z, okay? So, and then we apply our bounds and we have this. So how informative are the bounds? It depends on the extent of the misclassification and also depends on how people misclassify, how they misreport, okay? So as you can see here, if the misclassification is small, okay, the lower bound is close to the true value. The true value is the black one. The upper bound is the red one. And we can hit the upper bound depending on the dependence between the misclassification and the cost variable V. But if the alpha, the misclassification, the extent of misclassification is equal to 0.5 in the data, our bound diverge. So think about it this way. If everybody is misreporting, we can just flip the treatment and control group and then identify the parameter, right? So on the two extremes, we point identify. As you move far from the extreme and then you get to the middle, then you have no information. If 50% of people in the data, they are misreporting. That's why the bound diverge. Okay, but now, how about the true? How about when you just ignore that, okay, there is nothing, no misclassification in my data. I'm going to just ignore that and then estimate the MT as the derivative of the expected value of Y given the propensity score. So the green here is just if you ignore the marginal, that there is misclassification in your data, and then you want to just estimate the MT. Usually, the MT is not within our bounds here. And as you can see, in some extreme cases, you may be getting something completely opposite of the sign if you just ignore the misclassification in your data. Okay. So how do we compare our result to the late? Because we can do the same thing when we are looking at the late, the local average treatment effect. Okay. How we compare our bounds. So a quick response to this is the marginal treatment effect, what has been done, the lower bound on the PZ minus PZ prime is just the summation, half summation of these two quantities, the bounds that I derive. But what we are getting here is the maximum between the two quantities. So the max is always bigger than the half summation unless the two quantities are equal. So we have substantial improvement over the existing bounds in the literature. Okay. So now what happens if just if the misclassification is not done by people, for example, some administrative assistant is reporting the results, then it's just type in and then makes a mistake. So what happens to that case? We still have the same information. Can we tighten the bound if we know that it's just random? But if people are misreporting intentionally, like, okay, you go to the interview, you tell the manager that you have a college degree and they have no way to check that, then that can influence your wage, right? That they will give you. Because then in that case, the measurement error is not differential and endogenous, right? What happens in that case? So if the measurement error is completely exogenous, we can just back out from the first stage regression, the PZ function as the function of the propensity score that is reported and the rate of false negative and false positive in the data. False positive means that you don't have the degree, but you report that you have the degree. False negative is that someone has the degree, but maybe he doesn't want to show that he's smart. He just misreports. Okay. So in that case, if the epsilon is exogenous, it's done by the administrative assistant, then the false positive rate will be equal to the false negative rate, and then it will be equal to the misclassification rate in the data. In that case, we say that the misclassification is symmetric. Okay. So in that case, we're back to this. So the PZ function that we're looking for is identified up to this misclassification rates. So when I change this misclassification rates, then I get a set of functions, right? That's why I say I get this bound when we have this misclassification depends on only on the extent of misclassification. So in this picture, what I have is we know the true proportion of people who misreport, and then we, as a researcher, we fix the alpha bar. We want to see what happens to the identified set. So there is the true misclassification rate, and there is what I set for my alpha bar, the extent of the misclassification in the data. Okay. In the first, the alpha is equal to 0 and the alpha bar is equal to 0.1. So we get this bound on the marginal treatment effect. Okay. So this is the identified set. Instead of getting the single curve, we get a set of curves, but we still have informative bounds. Now we increase the extent of the misclassification. The true one is 0.1, but instead we say we don't know it and we say it's 0.3. And then you see that the bounds become larger. But now here, what's happening is the true misclassification rate is 0.3, but we set our alpha bar to be 0.1. Okay, like we are restricting too much this extent of the misclassification. Then we get our identified set here, and the true function is not even within our identified set. So it's a kind of sensitivity analysis, right? You play with this extent of misclassification rate, but if you set it too low, you may not cover the true parameter, and you are having the same mistake that people will have if they just ignore misclassification, even if we are doing partial identification. And if we set it correctly, okay, 0.3, it's similar to what we had here. We get in this bound. The true one will come the lower bound for the marginal treatment effect. Questions?
Almost done with time.
Almost done. Okay. So I'm going to show you quickly. I'm going to show some data. I want to show you how you can see this in the data. So this is an application on return to schooling in Indonesia. So this is higher secondary school, 10 years plus, okay, of education. So we look at the effect of that on earnings. And as I said, people miss reports when it comes to the education level, okay? And we first implemented the bound, okay, the empty bound that I showed you. Assuming that there is no misclassification, what do we get? We get this function here, okay? So here you can see this is like the V variable, the different values for V. And then you see that some people who face higher costs, the return can be negative. And people who face low costs, they can have positive return. But if I just take the average, I may not get anything. I may say there is no effect, no return. But this heterogeneity, you will not get that if you did not use this empty function. Okay. Now, when we add misclassification to that, what happens? Here we just had this single curve, which is decreasing. When you add misclassification to it, and we assume that the extent of the misclassification is 0.1, we get this set of curves. Okay, that's partial identification. But still, you can see that some people, they gain from school, some people they lose, and some people they in the middle. Okay, if we just take the average, you may not see that. Okay, so since I don't have time, let me quickly conclude here. I want to say something about this policy relevance. Like if we induce 20% of people to get the degree, what happens? So this is the question that the late may not be able to answer, right? We did that exercise here. We say, okay, let's say we get 8% of people who did not get the degree now. We get them get the degree, what happens, okay? So we see that if we move them and then they get the degree, the return will be between 30% and 40%. And I come back to the question that he was asking before about this function. So if we look at here, people who are here, they are the people who did not get the degree much. Most people are here. So if we move 20%, we are touching these people, right? So they face higher costs. That's why they did not get the degree. If you lower the cost, you may induce them and they will get the degree, right? So we're changing the distribution of the PZ function, but we are assuming that the empty function is still the same, right? But we're changing the distribution. We move people from here to here and see what happens to the return. Okay, so am I done?
Yes,
Okay.
because you are above time.
So, okay, let me conclude here. So in the paper, we derive bounds on the empty when there is misclassification. When you see someone in the treatment group, and you really don't know when the person is the treatment group or control group, just because they tell you, okay? So we show that if you ignore misclassification, you may have bias in your identification if you identify the empty. But if you try to take into account this misclassification, you lose point identification, but you can still derive some bounds that are meaningful. So that's the message here in the paper. Thank you very much.
Thanks, great talk. So a comment and a question. So this step that you said where at the end, the information on the response is informative about the distribution over the treatments. I think that's a very interesting thing that can happen. And for example, in the IV model, it's partly the reason that you can reject the notifier assumption, essentially, because the information from the response lets you realize that the assumption there are notifiers is not possible, and that's obviously tied up with the situations where the bulky Pearl bounds are more informative than the natural bounds, because because if you could have to, if there are notifiers, then they're going to agree.
Yeah.
A quick question here about in this example, what was the instrument?
The distance to college. Distance to college. Yes.
Okay.
So yeah, I didn't say it's the true distance. It's not like what Ismail was saying is proximity, whether you live in a corridor or county, it's the true distance here. And yes, you may still question the validity of the instrument here, fair, but we try to control for some observed characteristics I did not show here. So we abstract that from the treatment and do some kind of Rubin projection. We project out the covariates and then use the residual to estimate this curve. Yeah.
Excellent talk. Just a quick question, because I think you showed at some point that there is a screen curve corresponding to where you assume there is no measurement error.
Yes.
That can fall out of the bound.
Yeah.
Does that mean in that case you can falsify the assumption that there is no measurement error for the data set?
Okay, that's a good point. So this is because I know the true, it's in a simulation, right? I know the true, but in data, true data, I don't have this. I only can have my bound, and I don't have therefore. Oh, okay. So this is when you ignore the misclassification. Yes. So basically, it's like saying that my bounds here, right? The bound that we derive here. This one, right? If you ignore misclassification, you point to identify this as the true propensity score in the data. It can be less than this quantity, then yes. But it's the whole model. You cannot say it's just misclassification, right? It can be the IV, right? It can be one of these assumptions, right? So yes, the whole model, I would say, then we can reject.
Yeah.
So yeah, which is basically similar to the testable implications in the late framework that Ismail they have derived, right?
Yeah. On the other hand, I feel it's a little bit surprising because I think even if assume the IV model, it seems to me that there's no restriction on the instrument and the treatment. So.
Oh, okay. Yes, exactly.
Oh.
It's here.
Okay.
There is this monotonicity condition here that is implicit in the model through this specification. We impose the notifiers assumption.
So the threshold condition that he put here impose notifiers assumption. I have quite a few questions. I am not a fan of the late type of parameter, because Isa is not here because she also not a fan of the late. So my point is, if you are really interested to the parameter like the average treatment effect, and with type of misclassification, right? Yeah. So instead of looking at bounding the late that you do here, is that possible? What looks like the bound on the average treatment effect when you are in the presence of misclassification of the treatment?
So basically, you just use this, right? This bound, then you integrate over the AT domain.
So how this looks like compared to the usual Minsky-Rubin bounds?
With misclassification?
With misclassification. This is a question that I ask. And okay, the second thing is, in presence of misclassification, do we still get the testable implication a la back and Pearl type of
in the absence of misclassification?
In the presence of misclassification.
No. In the presence of misclassification, that's the kind of question that he asking here. We have this as testable implication if we say, okay, we plug in and say we ignore misclassification. So it can be, if I reject this, it can be either because of misclassification, it can be either because of the IV set of assumptions. So the testable implications are similar to back and Pearl's testable implication. That's why we cannot say if it's misclassification or the IV model. It's one of them. Yeah.
I see. The last question that I would like to ask is, again, going back to my discussion with Isa here. So if when you think about the example that you gave at the end, you say that if we induce people to have more education, how this is going to affect the margin, the decision. But when you do this experiment of inducing people to have more education, are you keeping stable the potential outcome?
Yes. So that's the assumption.
But is that possible? Could you just push people in an experiment to make people more into the education and keeping their level of ability the same?
So in the model, that's a good point. So in the model, I assume that this one here, sorry. Right. So I said this is the benefit function, okay, the interpretation. So it's kind of, I'm trying to change the benefit here compared to the cost, or try to lower the cost, right? If you think about the MT, basically it's like people at the margin. If I lower the cost for them, they may be able to go. Or if I increase this benefit function, they may be able to go. So trying to play with this exogenously, like a do type, but not trying to touch the potential outcomes. So that's the exercise.
Okay, I don't know.
But you are
that
saying that it's not
experiment.
possible to do this kind of.
Because if you think in the reality,
Yes.
one thing that you could do is, for example, reduce college fees.
Yes,
right?
right.
Something like that. But if you reduce college fees, people are gonna more invest into their kid. Maybe this could increase their ability. People are gonna respond to that. They will not fix everything when you move the college fees, or maybe having more professors, for example. And having more professors are gonna affect their ability. And so it's not clear to me that you could just have an external experiment that's gonna change only my decision to move or not, but gonna keep all my other unobservable state fixed or latent variable fixed.
Yes,
So
I thought that when we do this do calculus, right, we change it exogenously. My change, when I lower the college fees for them, they did not have nothing. They have nothing to do with that. It's me as a policymaker, right? I say, okay, now we lower the college fee for everybody, for some people, but it's exogenous, right? It's not that related to whether you come from low income family or this. You do that exogenously.
Let's talk that during the break. Okay, let's thanks Désiré for it. Thank you.